Hello, class, and welcome to week 2 of CIS 101 Intro to Computers and Their Uses. This week we'll be taking a deeper dive into hardware. So hardware, those are the physical components of a computer. We'll make sure to review some of those concepts. But before we do so, let's go ahead and take an overview on what we'll be covering this week. So computers, they often seem like a mysterious black box, meaning that they just seem like magic, right? We don't really know what's going on inside. We can't see what's happening. All we can really see, right, is those outputs, right? When we're playing a game, right, the screen, or when we're using certain software like Word, Microsoft Word, or Microsoft Excel, right? We'll see that application show up as well on the screen. So most of the time, the way we interface with computers is the screen, right? But we don't really understand what's going on behind the scenes. So this week we'll be working to demystify the computer and its system by taking a look at the hardware involved, and then also taking a closer look at what each of those parts do. Some of those core parts are the CPU, the processing unit. If you remember computer, that keyword is compute. So that's kind of what the processing unit is responsible for. There's memory, right? We need to save that data to use it in the future. And then also we'll cover input-output devices. That's your keyboard, your mouse, your screens. So a little bit of review. If you remember, hardware is the physical parts of the computer, the stuff you can hold in your hand. Sometimes that stuff, those parts are inside, right? That could be like your processing hardware, the part that performs the calculations or computations. Remember, keyword in computers, compute. There's a storage hardware that stores the data. That's your hard drive. Sometimes could be your USB memory sticks, right? And then there's your communication hardware, right? If you're going to connect to other computers or to a large network, famously, one that we know is the internet. If you're going to connect to that, you're going to need some special hardware to hook up to your Wi-Fi router, and so on. There's also the external hardware, right? Stuff that we interface with, the screens, speakers, printers, and so forth. Just to remind you, what is a computer? The four basic components or functions of a computer is that it'll receive input, so you kind of give it data. The computer will process that data. As we saw on the other slide, the unit responsible for that is the CPU, central processing unit, will process that data. And then we provide an output. So we take that input data and we output some useful information. So after it's been processed, it's called information, right? That's one of your quiz questions, actually, for week 1. And then we have storage. So one of the key parts, right, of any computer is that it needs to save the data so that we can use it in the future. All right, so as far as the new content for this week, we'll start with digital data. So first of all, a digital computer, what is that? It's an electronic device that processes data and performs calculations using binary data, zeros and ones. Okay, so digital computer, it's electronic, right? And if we go down to the core of its parts, electronic means it handles electrical signals. And if we simplify those electrical signals, whether we're talking about high voltage, low voltage, uh, that doesn't really matter. We're just going to simplify it to on or off. Is there an electrical signal or is there not? So all computers today are digital computers. When we say binary data, binary just means two parts or two alternatives. In the case of computers, like I said, it's on or off, or if you want to say off or on, vice versa. And we use numbers to represent those states. So actually off is represented by 0 and on is represented by 1. And going back to Ada Lovelace, right? The first computer, all we could think of it doing was simple calculations, especially if we're only talking in the language of computers, which is zeros and ones, right? How can we use zeros and ones to represent audio, video, right? How can these zeros ones translate to what you see on your screen, whether you're playing a video game, using a software like Microsoft Word, Excel? How can these numbers become that, right? Well, Ada Lovelace, she kind of was the first to propose that even though computers work with just numbers, these zeros and ones, if you kind of layer them together, you can actually do some really impressive things. You can use these numbers to represent more complicated things. But at the most basic, computers are digital. They use binary data, and binary means two states. So off or on, 0 or 1. And you can see this little table here, right? On is 1, has an electrical charge. No electrical charge is off, and that's represented by a 0. All right, so binary, the language of computers. So as we covered in the previous slide, binary is how computers really talk. It's the language that they understand. So all of the data that you input to a computer is really read by the computer as binary data. So if it's input from a keyboard, from a software program, the video game you're playing, the app you're using, whether it be on your laptop, right, or on your smart device, your USB drive, the game controller, your mouse, your touchscreen, whatever is providing input to that computer, really the computer is reading it in binary code. We sometimes call this machine code because, like I said, binary is the natural language of computers, of machines. So those zeros and ones, those are the smallest unit of data. It doesn't get smaller than on or off, electrical signal or no electrical signal. We call that smallest unit of data a bit. A bit is actually a short form of the word binary digit. So digit means number. A binary number is 0 or 1. So if you kind of put binary and digit together, the beginning and the end, right, it's going to be a bit, is the short way to say it. So yeah, 0 or 1 is a bit. Remember, represents off for 0, on for 1. And yeah, that's how the computer interprets those electrical signals from those electrical components. So we can actually represent text in binary, and this is how we do. This is how we encode text in the real world. So the real world of computers. So hi, just two letters, very simple. It turns out in machine code or in binary, it's actually really complicated. So the word H in this system called ASCII, that's how you pronounce that. It stands for a much larger acronym, but most people refer to just as ASCII. So these letters in the English language can be represented by numbers. So simple enough, the letter A, we start with 1, all the way to the letter Z, right? Our 26th letter is going to be represented by the number 26. Um, so those numbers actually, 8, 1, 2, 3, 4, 5, 6, 7, 8, all the way to 26, those can be represented in binary. So the number 8 is actually 0, 1, 0, 0, 1, 0, 0, 0. So it takes all those binary digits to represent the number 8. If you're curious how that actually works, there is some math involved. Every digit here is actually a power of 2. So this is like 2 to the power of 0, 2 to the power of 1, 2 to the power of 2. It gets a little complicated, right? But if you notice where the ones are at, that's going to tell you where to do your powers. So this is the 0, 1, 2, 3. So 2 to the power of 3 is 8. And then here, let's see, 0, 1, 2, 3, 4, 5, 6 to the power 6. These digits, they're a little bit more complicated, but for the most part, you just take this first part. And so 2 to the power of 3 is 8. You don't need to remember that. Just wanted to give that extra explanation for anyone that's curious. All you need to know is that numbers in our decimal system, for example, 1 through 26, can be represented in these complicated binary codes. You don't need to learn how to translate those. If you do take some computer science courses, they actually do teach you how to convert from these two systems. But yeah, so the letter H would be 0, 1, 0, 0, 1, 0, 0, 0. And then the letter I would be 0, 1, 1, 0, 1, 0, 0, 1. So together, the letters H and I would be encoded by these two binary numbers put all together. So HI would be 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1. You don't need to learn how to read like a computer, right, for this class. It's totally fine if this is strange to you. We will have a little exercise in our lab where you get to do some translations, of course, with the help of a table. So you won't have to be turned into a robot and start reading machine code. Don't worry about it. An example of images to binary, right? So if we have black and white images, right? The black pixels, right, could be, in this case, zeros, where we turn off the pixel. And then the white, right, where we turn on the pixel could be ones. So just an example of how you can also encode images, right? So if you look at those really old Super Mario games, right, it is possible to represent those images in binary. If we start to add color, then we're going to need more binary digits, right? We have three colors here, right? So we're going to need extra binary numbers to represent each color. If you notice here, a white square is a 1, 1. So everywhere there's a white square, we can represent it as a 1, 1. A red square here is a 0, 0. Orange square is a 0, 1. And then a yellow square is a 1, 0. The more colors you add, the more digits you're going to need. So if you add 10 colors, right, you're going to have to add much longer numbers representing each square. Again, not something required for you to memorize for a quiz or for this course, just some examples. Notice there's no star on these slides. So the stars are the ones you need to remember. So here we have a star on this slide, so let's keep going with bits. And then we'll also talk bytes and memory. So as we said, a bit is the smallest unit of data that a computer can read. Well, computer reads in zeros and ones, so a bit can either be a 0 or a 1 because it's binary data. So the word high, like we saw in the previous slide, is represented by this very long binary code. If you notice, it has 1, 2, 3, 4, 1, 2, 3, 4, 9, 1, 2, 3, 4. I think this might have a typo. This should have just been 16. So let's pretend there's 16 digits here. I'll make sure to correct that in the slides. But yeah, let's say there's 16 digits on this. That would mean it would be 16 bits. In this case, there's an extra digit, so it's actually 17 bits. But again, it should only be 16. I'll make sure to correct that. So yeah, this code right here is 17 bits. When you go to the slides, I'll make sure it's only 16. Uh, but the unit you need to remember beyond bit is bytes. So anytime there are 8 bits, we call it a byte. So if there's 16 bits, that would be 2 bytes. So the word high would be 2 bytes. So the reason we cover bytes as well is because bytes are commonly used to measure amounts of data. You've probably heard kilobytes, megabytes, gigabytes. So if you have a smartphone, right, you might shop around and you want to have more bytes, more gigabytes in the case of most smartphones today. Because the less gigabytes, right, the less data your phone can hold in its storage components. So yeah, bytes are often used to measure the size of a document or photo, so your files, your photos, and they help us measure the storage capacity of a computer's memory. So remember, a computer could be your laptop, right? How much storage does your laptop have? But it could also be your smartphone. How much storage does your smartphone have for all those pictures and apps and so forth? And if you run out of space there, right, you can always save your data, right, elsewhere, right? Maybe to a memory stick or to the cloud, right? And remember, the cloud exists physically somewhere, right? It's probably a computer that transmits your data through the internet. So no matter what we're talking about, when we're talking about memory, it's probably going to be attached to some kind of physical computer. So the cloud, it's not just a cloud, right? It actually exists in real life in the form of a computer, maybe 1,000 miles away, maybe millions of miles away. So big bytes. So we have bits, byte, kilobyte. So this is kind of just an idea of how we translate from the smallest unit of data to some of the bigger ones here at the bottom. So bit, the smallest unit at the top of the triangle. You don't have to know this, but 4 bits, we call it a nibble, funny enough. 8 bits is a byte, as we covered in the previous slide, so you just need to know bit and byte. If you have 1,024 bytes, so just roughly 1,000 bytes is going to be a kilobyte. Roughly 1,000 kilobytes is going to be a megabyte. Roughly 1,000 megabytes is going to be a gigabyte. Roughly 1,000 gigabytes, terabyte, and they go even bigger. We got zettabytes, yottabytes. Those are really, really big. For example, I have a memory drive a storage drive for my pictures and for files. Whenever my computer, right, doesn't have enough space for those things, it takes about, I think, 2 terabytes. So that's a lot of memory. And the reason I need so much memory is because I take a lot of pictures, right? And these pictures, they're from a digital camera, one of those professional looking cameras. So each of those files is really big. So I'm going to need terabytes. My phone has gigabytes, so it can also hold a lot of photos. But when I'm talking about the thousands and thousands of photos, I'm going to move them to my terabyte storage device. And then when we're talking about documents, like your Word documents, maybe the homeworks, right, you submit, that's probably going to be in kilobytes. So they're not very big, right? Because we're just handling text. So yeah, the more complicated the file, the document type, the more memory it's going to require, the more bytes to encode that data. But it doesn't matter if it's a picture, if it's a document, if it's a spreadsheet, all of it can be represented in bits, and those bits are really just zeros and ones. That special machine code that computers can understand. All right, so let's cover the central processing unit. So that's going to be the first piece of hardware we cover in this class. So what exactly is a CPU? Well, a CPU is short for Central Processing Unit, and it executes instructions from programs. It processes data and manages tasks that keep the computer running. So they call it the brain of the computer, or the control center. It's really what calls the shots and makes the computer actually do what you want it to do. So processing unit, right? Really, it makes this possible by performing calculations, right, on that binary code you feed it, because it doesn't matter what kind of input you give it, whether it's on your touch screen, whether it's on your mouse, you click a button. That's all just binary code. So the computer takes that binary code, performs certain calculations. It gets very, very complicated. In this class, we'll kind of just cover, the very surface level information. But yeah, it takes in this code, does some computations, and then it shoots out a transformed version of that code in order for the computer to now perform certain aspects that you need it to do. A CPU is a type of chip. And if you remember with the advancements in transistors and circuits, we went from having these giant computers where they would take up an entire room. Well, with some of the chip technology we have today, you can fit an entire processing unit on a single chip, so on a very, very small surface area. So those are thanks to the advancements we had in electronic technology. So here's a look at a CPU. So here on the left, you can see it's a metal component, has some semiconductor materials in there as well. You don't need to know that. Notice there's not um, a star on this one. There should be a star on CPU. I'll make sure to add that on the slides. But yeah, you don't need to know what it looks like, what it's made out of. But here's just a diagram so you get yourself an idea of how these things work. So the CPU takes input, it runs it through these individual components inside. We have a control unit, an arithmetic logic unit, a memory unit, kind of some of those core components, right, of a computer. The four core components are represented here as well in the CPU. So we have input, output, memory, and then processing, right? Those are the four components. So yeah, CPU is capable of doing all four of those things. So when we're talking computers, let's say you're on Word, right? And on Word, you click New Document. That button will send input to your CPU. That CPU will interpret that input in machine code. It will process that machine code, and then it will output, right, some information back to the computer and say, hey, when they click blank document, I want you to open up a new document on the screen and show them, right, all the information they need for that document. So the things providing input to the CPU are going to be the software programs, which we'll cover in another week. We'll take a deep dive into software, and we'll also learn how to use certain software like Word, Excel, maybe some Google Suite applications as well. We'll also talk about web browsers and how to surf the web. So things that are really important to us. But before we get to the cooler parts of the class, we do have to demystify how these computers work. And at the end of the day, computers really their language is binary, zeros and ones. When they take this binary input, it transforms it into output that's more useful, right? So on my screen, I have words, I have pictures, I have that star on the right, I have these colors. And in this video, you're hearing the sound of my voice, right? And you can see the images moving because it is a video, right? This is many images put together. This is all made possible by the computer taking in inputs, processing them, and providing useful information as output. So yeah, that'll be all for the first part of this week. We'll be covering some more hardware components in the next videos. For now, we'll talk about the lab and what you have to do. You'll kind of get your hands-on experience with converting from text to binary code, which yeah sounds a little bit tricky. I'll make it simple enough just so that you get some a chance to really understand how computers read text and letters and words. And we'll also kind of think about how the direction of technology in the future, right, affects how much data that computers have to process. So we'll cover all of this in the lab.